Okay, everybody, welcome to class. Happy rainy Wednesday. Today we are going to finish chapter 10. There's not very much left. We've really only got 2 learning objectives left, and we've kind of already talked about them. One is we're going to say a little bit more about non-equilibrium diagrams. We're going to say a little bit more about steel. We started talking about it. I'm going to formalize that a little bit more. But more than likely, we'll then have a chance to answer broad questions about the stuff we've covered. And if there's no more questions in class, then we'll just move to chapter 9. And I'm okay doing either. If you want to spend the whole class asking questions, we can do that. Or we can move to chapter 9. Doesn't matter to me. There's a review session tonight from 5 till 7 that I will be hosting. So I'm not going to prepare any material. I'm just going to come and project the study guide and say, what would you like additional clarification on? So if you have specific questions, come with them ready to ask. The TAs have another review session tomorrow from 6:15 to 7:45, I think they said. Both of those should be taking place in this room. If for some reason this room is full, which it shouldn't be, then we'll just leave a note on the door saying where you can find us. Okay? So that said, let's get started. I'm going to say a little more about non-equilibrium phase diagrams because the assumption up until now is like these phase diagrams they're pretty handy, right? They tell you where you can find different phases, and that's pretty awesome. The whole catch, though, is that it assumes that you can reach equilibrium, and that's hard to do sometimes. Here's a great example. This is the phase diagram for Y2O3. That's yttrium oxide, or we call it yttria. Any metal oxide, if you just get rid of yttrium, like with the M at the end, if you just say yttria, it means yttrium oxide. Like alumina is aluminum oxide, right? So we would say this is the diagram between yttria and zirconia, right? Or Y2O3 and ZrO2. Why is this a great example? For a couple reasons. First off, maybe you've heard of before, like cubic zirconia. You've heard of cubic zirconia before? Yeah. This is like the fake diamond, right? It looks a lot like diamond, but it's not. It's zirconia. It's ZrO2. So on this phase diagram, on the x-axis, we've got the mole fraction of YO 1.5. See what they've done there? The normal formula for yttrium oxide is Y2O3. They've plotted it as YO 1.5 for reasons that will be more clear in a few chapters. Basically, you're thinking about every zirconium atom, you're replacing it with an yttrium atom. And so that's a 1-to-1 substitution. So that's why they're plotting this as YO 1.5. So for every half formula of Y2O3 in mole percent. That's why they're plotting it this way. This would be cubic. It starts out as monoclinic. Pure zirconium oxide is monoclinic phase. That's a type of structure that we're going to learn about in 2 chapters, right? And when you get it warm enough, you reach this point at which it will transform, just like iron went from one low temperature phase and turned into another one at high temperatures. This turns into what's called tetragonal, T, zirconium. And if you go high enough, it turns into that cubic, right? Cubic zirconium. Crazy high. That's in Celsius, right? 2,400 Celsius is bonkers temperatures, right? We pride ourselves in my lab for having some extremely high temperature furnaces, and the highest one we have goes to 1,800 C, right? To get to those temperatures, you're looking at really exotic ways of making this stuff, okay? So when they say that you've got a diamond ring, right, but it's not diamond, it's cubic zirconia, how on earth are they making that? Well, there's lots of things that they can do. For one thing, you could heat it up to 2,500 Celsius, let it equilibrate so it's in the cubic structure, and you could try and quench it. And literally, they take it and they open the furnace door, you grab it with some tongs, and you drop it into liquid nitrogen, right? All sorts of things can go wrong with that. You're changing it over 2,000 degrees Celsius. So remember things that they expand typically. So when you drop it and you make it shrink rapidly, what do you imagine might happen? Anybody taken a hot pan, a casserole dish out of their oven and then put it in cold water? Yeah, it's toast. It's gone, right? That's typically, so I don't think that you can quench cubic zirconia. I'm just going to go out there and make my prediction that that won't work. But what you can do is use the phase diagram and say, oh, well, what's slick about cubic zirconia is that it exists over this really big range. All this region out here is all the cubic phase. So if you dope it with, 18% by atomic percent of YO 1.5, so 18% of the zirconium atoms have been replaced by yttrium atoms, all of a sudden at room temperature, the cubic phase is actually stabilized. So cubic zirconia diamonds are not cubic zirconia, I'm guessing. They're probably cubic zirconium and yttrium oxide mixtures, okay? That's not even the most interesting part. Quenching is one thing. That's one way to skip these low temperature phases that are thermodynamically stable. You can try quenching, and sometimes that works. But sometimes the kinetics are just sluggish. For example, here, if you heat something up and you add enough zirconia that, let's say you're in this region, right? This is a two-phase region. They're nice. They labeled it for us. It's T plus F. So you've got the tetragonal phase and the cubic, which is called the fluorite phase, which we'll learn about fluorites in a few chapters, right? But the point is, this is a two-phase mixture. You should have two different phases both existing. And when you cool it down, there is a special reaction. What reaction happens along this line? What reaction is that? Well, this is the point of this reaction. The reaction happens all the way along here, but this is the point where it happens to completion. You've got a single phase turning it into two solid phases. What do we call that? That is a eutectoid. So this is all along here, the eutectoid reaction, meaning any of this T phase that is present all along here, any of that that's there is going to transform, right? Yeah, it's going to transform into a mixture of these two things. So here, you've got T plus F, and when you go below that line, any of the T that you had should transform to monoclinic plus the fluorite. Or in other words, you should have no what's called tetragonal phase. What's amazing about this, in this ceramic system, this happens at a relatively low temperature, 600 Celsius or so, and so the kinetics for this are sluggish, right? You don't have a ton of heat at 600 Celsius. It's not that hot, and so you can skip this reaction. It's as if this whole part of the diagram just disappears. It looks instead like this, like your diagram just continues down. Like all this stuff is gone, and you just have this line gone, and you just keep your T plus F phase. Why do we care about that? This allows us to have one of the coolest ceramic materials of them all, which is zirconia stabilized, yttria stabilized zirconia, YSZ. Actually, let me do a different picture. Yttria stabilized zirconia, what do they make out of them? Like cutting kitchen knives. Maybe you've seen these. You can buy them in any nice store. A ceramic knife in the kitchen sounds like a bad idea because if you drop this while you're cutting your lovely tomatoes, typically ceramics are just going to shatter to a bazillion pieces, right? Why would you want ceramics in the first place? Like, is this just doing something because we can? Or is there any point to this? Yeah, in the back.
Ceramics, when they break to an edge, are really sharp and really hard, so they keep their sharpness for a long time.
You're halfway there. They do stay sharp, and you can get them sharper, and they stay sharper longer, but it's not because they break it in a nice edge. That's a good guess. Why do you think we can get a sharper edge on a ceramic knife? So you always answer, so let's go with Carlos. Ceramics are harder. The harder it is, why does that mean you can get a better polish on it? If it was, for one thing, if it flexed, that's going to mess it up. But if it's more ductile and prone to deformation, it's not going to keep that edge, and it's not going to be able to form the edge quite as sharp either. The harder something is, the smoother the polish you can put on it. So ball bearings, another great example. Silicon nitride ball bearings can be, even though it's round, you can polish that ceramic to crazy, crazy smooth levels so you get the best ball bearings, right? Sports cars, really nice skateboards, bikes, these have ball bearings that are made of ceramics as opposed to metals because they get smoother and they stay that polish longer. Yeah, question?
Just thinking, like, is that because you can get like smaller amounts of the element at like an atomic level? You can have like a very fine point because like it holds together stronger.
Well, think of how you make a blade in the first place. You shave away atoms, right, in either large amounts or small amounts. And if you have a hard material that's harder to shave away, then you're removing fewer at a time. And so you're going to get a nice, clean edge. It's harder to do. It's way harder to do. But the edge is better once you get it. So ceramic knives are great. If you haven't cut with one before, give it a shot. It'll blow your mind. You'll never go back to cutting tomatoes again with a regular old boring knife. Right? Tyler?
Does the expansion of the metal and contraction of the metal when you like run under hot water versus the ceramic knife also?
Good question. So what do you guys think? Going back to chapter 2, this is a good review question. Which one should expand and contract more, a metal knife or a ceramic knife? And what's your rationale? So turn to your neighbor and tell them what you think. This is a perfect exam question. Okay, what do you guys think? Should a metal or a ceramic expand more or less? Like, what's your rationale? What do you think? You have to remember your name. Landon.
So the metal would expand more because if you look at the graph of energy versus
Yep.
the ceramic one has a deeper trough, which means it wouldn't expand as much as the metal would because it has shallower.
Why does a deeper trough mean less expansion?
It takes more energy to move it.
Not quite right. It's a good guess. Let's go back to these things. Pick a deep trough, right? So here we had these three, right? Ceramic, metal, polymer. The one that's deeper is more symmetric. Meaning if you heat it up, what you are doing is when you heat it up, this is absolute zero. It's going to occupy this lowest energy level if you take all the heat away. If you give it any bit of thermal energy, what it really means is that it's sloshing, like let's say you give it like 5 EVs of thermal energy. It's sloshing between these values, right? And if it's symmetric, then the average value is still right in the middle. So as you heat it up, it's not really changing. But on these ones, you heat it up 5 EV, its average value between this point and that point is clear over here, so it's expanded. That make sense? So the deeper the potential well, the more symmetric it is, the lower the thermal expansion. So ceramic knives, yeah, they expand less. Ceramics in general are about an order of magnitude less thermal expansion than metals. But they're typically really, really intolerant to any sort of strain. If you bend a ceramic a little bit, it just snaps, whereas a metal can deform, right? Maybe even elastically. Maybe it can bend and then bounce back. Ceramics cannot do that. What's amazing is that in this system with yttria stabilized zirconia, go back to it, they can. And here's how they do it. It's pretty amazing. They call this ceramic steel. You can buy this stuff right now. How it works is you've got this T plus F phase up here, but you cool it down, nothing even crazy. You just cool it down, and this phase doesn't form because it's just sluggish. Okay? So what you have is you have T plus F, where all the T phase, the tetragonal phase, thermodynamically speaking, wants to turn into M. Okay? It wants to turn into M. But that process involves a change in volume. Right? These phases don't have to occupy the same volume. And in this case, it has to expand a little bit. So this is amazing. What happens, let's say you've got a ceramic, right? And there's a crack tip. Right? So this is your material. And inside of this, you've got lots of T, and you've got lots of F. So let's say that you've got a little T region, right? Right there. As the crack gets close to it, this T region is just itching to expand and turn into M. It's been compacted by all the grains around it, and that didn't allow it to expand. That was like a kinetic barrier it had to overcome. It had to shove the grains around it out of the way. But if a crack shows up, it's just going to expand. And it puts a closing pressure on the crack, right? They call this transformation toughening. It transforms from T, the metastable phase, into M, the thermodynamically stable phase, in the vicinity of the crack and puts a closing pressure on that crack. So these things have a fracture toughness, which we will learn all about next chapter. Fracture toughness, comparable to some crappy metals, which is light years better than most ceramics, right? So this is still brittle. It will still break if you drop it, maybe. But it's a whole lot better than if you made a knife out of, say, pure alumina. Alumina, you can make it equally hard, equally sharp, but if you drop it, it's much more likely to break than this, because this has this transformation toughening mechanism, where again, once it transforms, it's a little bit bigger in that M phase. I have to exaggerate it, but that puts a closing pressure on the crack. This is pretty rad. You guys don't seem amazed. This is amazing. Somebody's jazzed out there. This is pretty amazing. So all sorts of things. If you see, if you have a ceramic that you just can't get around, when do you use a ceramic? The answer is never. If you can avoid it, never ever use a ceramic is really the answer here. But if you have to use it and you have to have some toughness, YSZ, yttria stabilized zirconia, or transformation toughened zirconia, same thing, is maybe something you should consider. It's a pretty awesome ceramic material. Okay? Let's keep going. So basically, you have to, in order to get this effect to happen, you could not take pure zirconia and get transformation toughening, right? If you cool this down, the kinetics are too fast. This transforms at a high temperature. So kinetically speaking, it will all transform to monoclinic. You don't get any benefit there. You have to add typically somewhere in this range. I think it's like, what have I got written? 3 to 9%? 3 to 7% calcium, or if you're doing yttria, it's 6 to 13. So somewhere in this range, if you add that much yttria, then you get the toughening effect. Okay? Just a quick note that we've talked about binary mixtures so far. Now, some of those mixtures have been things like this. This is a binary mixture. On this side, you have pure potassium chloride, KCl. On this side, you've got pure MgCl2. So even though there's 3 different atoms, we're only varying the ratio of those 2 things as formula units, right? Pure KCl, pure MgCl2, and these are mixtures between them. If you want to vary more things than that, you have to get more complicated phase diagrams. We call these, if you have 3 components that you're going to vary, ternary phase diagrams, and we won't be testing you on these in this class. Just realize that they're out there. Many materials that you're interested in, steels. Steel, we talked about, it's iron and carbon, but then they add all sorts of other stuff to it. Chromium, if you want stainless steel. Molybdenum, if you want, chromoly steels. So in that case, your diagrams get a lot nastier. Any 2 of these sides, say from A to C, looks like a regular binary diagram, right? That looks like a regular binary eutectic. But between A and B, it's going to look different. B and C, it's going to be different. And you have to have a 3-dimensional image to bring it all together. So what's the most common way of reporting these things is not to show you a nasty 3-dimensional image. It's instead to do temperature slices, where, again, you will not be tested on this, but a typical ternary phase diagram would look something like this. It'll show you, it's like a topographical map. You'll see different temperature regions, and it'll show you where different phases can be present. By the way, now that you have 3 components, what's the largest number of phases that you can have in equilibrium? Well, let's do Gibbs phase rule. P plus F equals C plus N. Okay? Let's assume that we have no degrees of freedom. So the one spot on the graph where you can't change anything, we're going to try and maximize the number of phases that can be present. Well, now we've got 3 components. Let's assume we're doing it just against temperature. So our number of non-compositional variables is just 1. We can have 4 phases in equilibrium, right? So it's more than just 3 like we've seen on our binaries. You can have 4 different phases in equilibrium. If you move to a 5-component system, you can have, if you have a 4-component system, you can have 5 phases in equilibrium. This is pretty rad, okay? So the point is, these things get really nasty and really complex and hard to visualize because we can see and think in 2 and maybe 3 dimensions, but 4 dimensions? How do you even show that? It gets hard, right? So you have to do some tricks to make it easier to visualize, and we're not going to cover those in this class. Just realize that they're out there, okay? All right, let's spend the rest of this chapter talking about steel. This is the steel phase diagram. This is something you should learn how to draw most of these parts, or at least have it on your note sheets, because most of these things are pretty important. So let's draw a few of them. First off, if you start out with pure iron, it's in the ferrite phase. This is ductile. It can be bent really easy. It's the same wire that I made the demo out of. And when you heat it up, it transforms at 912 C to austenite, the austenite phase. Now, which one can accommodate a greater amount of carbon dissolved into it? Can you dissolve more carbon into austenite or ferrite? And how does the diagram tell you this? This is weight percent carbon on the x-axis. Which one can dissolve more carbon? Definitely austenite. Ferrite has a maximum solid solubility. This is a single phase over here, this little sliver. And the maximum solid solubility is 0.022 weight percent carbon. If you add more carbon than that anywhere over here, you start to precipitate Fe3C, cementite. You start to form another phase, okay? Meanwhile, austenite, it can accommodate all the way out to 2.14% carbon and be one phase. So it can dissolve, 100 times more carbon, okay? Why do you think that is? Maybe turn to your neighbor. Why do you think austenite can dissolve so much more than ferrite? Okay, what do you think? What's so special about austenite that it can hold 100 times more carbon without precipitating a new phase? What do you think? Yeah.
When you change the crystal structure, you provide more areas where carbon can get in there and travel it.
Yep. If you look at these diagrams of the 2 different crystal structures, we haven't learned about them yet, but these are the 2 different forms of iron. The one on the left here, is BCC. That's the room temperature one. And the one on the right, FCC, at first glance, it's not obvious why one would accommodate more space. But when you take into account that carbon is a tiny atom, there's actually more spots that you can stuff it into that FCC lattice. Quite a bit more. What are called the interstitials, the spots between atoms, are just bigger. We're going to learn way more about these in a couple of chapters. So austenite can accommodate more. And then when you cool these things down, if you cool down right at 0.76, a number that you should be aware of, 0.76 weight percent carbon, you will go from pure austenite, a single-phase material, to a mixture of ferrite and cementite. Okay? What do we call that reaction? Eutectoid. Right? Eutectic would be a liquid turning into two solids. A solid turning into two different solids, that's a eutectoid. Okay? What will happen if I cool down just to the right of this? Along this gray line, say. If I cool along that line, what will I form before the eutectoid reaction? We form pro-eutectoid, not ferrite. Ferrite would be over here. Pro-eutectoid cementite. Right? We're going to form pro-eutectoid cementite over here. How much do we form? If I had to do a quick lever rule calculation, just before this reaction, how much cementite have we actually formed? You could do that. You could say, all right, cementite's the phase on the right, so I want to take the left-hand segment of the little line from here to here, right, and divide it by the total length of this line. So the total length is 6.7 minus 0.76, and this little segment would be 1 minus 0.76. So you don't form very much. You're still almost entirely austenite. Where will that cementite form? Where does it want to form? Where does it want to form? Yeah, what do you think?
It's like in between the grains of austenite.
Yeah, so if you initially had grains, for some reason, it's not letting me draw on that, but just above that eutectoid temperature, if these all used to be austenite, where you're going to form the cementite is along the grains. Somebody tell me why. So this will now be our cementite forming along these grains. Why does it form on the grains? Why does it form on the grains? Yeah. For one thing, there's more room, right? That's not the only reason. There's an energetic reason. Is it entropy or enthalpy? If it all consolidates to one spot versus being, say, dispersed all through the lattice, that doesn't seem like an entropy driving force. Being dispersed all over the place seems more disordered than coalesced in one spot. So it's not entropy that's driving it. It must be enthalpy. What does enthalpy have to do with? Bonds, which are the reason why you have surface, not tension, but energy. So again, if this is a grain boundary, we said that Zoe here would love to have someone sitting next to her, but she got nobody here, right? So that comes with an energy cost. This whole surface costs energy, and this whole surface costs energy. So if you're going to form a new phase, why would you create new surfaces right in the middle of an otherwise happy section of material? I mean, you will if you have to, but if these atoms in the middle that want to form the new phase are able to diffuse to a grain boundary, they're going to do it because you're going to form a surface energy. Why not replace what already had a surface energy? Does that make sense? So this can only happen at high temperatures, right? Atoms have to be able to diffuse to the grain boundary. And we're talking about pretty high temperatures. We're above, typically in like the 900 to 1,000. That's getting pretty hot. So things can, if you do it slowly enough, they will form along these grain boundaries. What happens if you do this really quick or it happens at low temperature? How would the structure look different? Yeah, you'd have speckles, basically. You would have your grain boundaries from before, and you'd have speckles of your cementite phase. If this happened at low temperatures or really quickly, you'd expect that. But thermodynamically, they'd like to start coalescing, and that typically means along grain boundaries. Any questions so far? Yeah. So steel, we're going to talk way more about that. Non-equilibrium cooling. If you quench these, quenching steel, we have a whole chapter on it later on. Chapter 11 is quenching steels. There's there's this software I'm going to show you real quick called MapMatch, which is pretty rad. You guys as engineers should be aware of it. It's free to use. What's cool about it is you can go here and you can just type something like steel, right? I want to know all the different types of steels that are out there, and what this will show you is every steel that is on their database, which is not all steels, and they have 21,645 different types of steel, right? From 175 different suppliers, and each one of these is different in some slight way. So this one, it'll tell you the composition, right? If I scroll down enough, It'll tell you what it's actually made of. Like, here's our composition. It's mostly iron, a little bit of carbon, but all this other stuff. This one happens to have almost 20 weight% chromium added to it. The point is, there's a bunch of different compositions, and there's a bunch of different ways of quenching steel, and that's why we end up with 22,000 different types of steel just on this website alone. Okay? So quenching steels, you can get enormous variety in the microstructures, right? As you go from this guy to that guy and everywhere in between, these all have different properties. Maybe you want like a really strong steel where you just prioritize yield strength and hardness, right? But you don't care about ductility. Maybe you really want ductility. Maybe you want somewhere in the between. Maybe you want thermal expansion to be tuned. You can tune all of these things as you change composition and, importantly, quenching as well. So hold that thought. We'll come back to it in Chapter 11. Other questions about this so far? Okay, what if you go to the left? To the left of the eutectoid point, we call these hypo-eutectoid steels versus hyper-eutectoid steels. Hypo-eutectoid steels, if you cool down right here, what is the pro-eutectoid phase that forms along here? It's going to be pro-eutectoid ferrite, okay? And it's going to form on the grain boundaries just the same, okay? In either case, no matter where you are along here, once you cross this line, that's the eutectoid reaction. Any austenite that's still available, even if it's only 1 or 2%, all of that must transform to a mixture of ferrite and cementite, and it's going to do so by forming the lamellar structure, right? These layered structures, unless you quench it fast as hell, and then you get a different thing, which we'll learn about later, okay? Any questions on this? Making sense? Yeah. Effectively, they do it via trial and error. Theoretically, you could potentially calculate, right? For example, if you knew how big your grains were to start with, let's say you're trying to make a glob of A react with a glob of B. If you know how big your grains are, right, the globs of material, then you know roughly how far atoms would have to diffuse to react, for example, to form some new intermediate. If you know how far that distance is, we know how to model diffusion distances with things that we'll learn in a few chapters in diffusion chapter. So theoretically, you could estimate how long it should take for reactions to go to completion. In practice, it's just by experiment. They just try a few things and they see. They see, is there leftover reactants or not? Yeah, unless I say otherwise, you assume it goes to completion. Or unless I give you like a clear giveaway, like you hold something for a short time at a low temperature, that's a pretty obvious thing that I'm saying, well, maybe precipitates form. They don't make it to the grain boundary. If I say, if you then hold that for a really long time, what would it eventually look like? Well, that's pretty obvious that I'm saying that it's approaching equilibrium. Okay? Yeah, question?
Which side was hyper and which side was hypo?
Which side's hypo, which side's hyper? To the left of the eutectoid is hypo. To the right is hyper. Hyper sounds like it's got too much of something. Like if I give my kid too much sugar, he's hyper. It's got too much. In this case, you got too much carbon. It's on the too much side. Hyper eutectoid, hypo eutectoid. Yep.
Is there a reason the graph stops at 6.7?
Yeah, great question. It is a line compound. Why does it stop there? Because all of your useful steels, I think I've got it here. Yeah. So for one thing, irons are up to 0.008 weight percent. If you go beyond that carbon, 0.8%. No, that's already in percent. 0.008. Basically, if you add any carbon to it, it stops being iron. If you're between that number and 2.14 weight percent, these are your steels. And anything above 2.14 are your cast irons. All the way up to about 6.7, and you never go, actually they only go up to about 4.5. And we just don't make things that we call steel beyond that. Iron carbide might be useful for a lot of things, but we don't call it steel anymore, or even cast iron. And then even within steels, you've probably heard of like low carbon steel, medium carbon steel, high carbon steel. It's basically saying where you are between these two ranges. Are you on the low end, medium, or high end? Okay? So a high carbon steel is going to be hyper-eutectoid, and along the grain boundaries, you're going to find cementite. Whereas in a low carbon steel, along the grain boundaries, you're going to find ferrite. Ferrite is soft and ductile because it's a metal. This one's a ceramic. What do you think? Is low carbon steel or high carbon steel more ductile? You've got something that's either really brittle along the grain boundaries or really ductile. Grain boundaries is typically where things slide past each other to get deformation. Hypo-eutectoid to the left, the low carbon steel is going to be way more ductile than high carbon steel. High carbon steel is going to be much harder. So if you're making tools like dies or tools, you're going to make them out of high carbon steel. And there's other reasons. We haven't even talked about dislocations yet, so we'll come back to that later. A hand and then a hand.
Do we just not go above that 6.7 because it just becomes too brittle at that point?
For steels, yeah, it's way too brittle. For us, these are happening at such small amounts as it is. If you went all the way to pure carbon, the region that we care about would be like tiny on the map. So they just draw just the region that we care about. But it does continue. You can go all the way over. It's just maybe those aren't interesting engineering materials, and these definitely are.
Does it just become so brittle that it's useless? Or
As you move all the way over, pure carbon would be graphite at room temperature, right? Or metastable diamond, which have great applications. They're just not steel. Sam?
So when you have, we're talking about the ferrite plus that cementite, when you have
Okay.
austenite plus cementite, is that going to be harder than the ferrite?
Is it going to be harder?
Yeah.
So there's so much that dictates hardness as it relates to the microstructure. It's not going to, but I'm going to wait till we get to chapter 11 to delve into the reasons why. Yeah.
If you're looking at this, either of the two cementite regions,
Okay.
how would you use the lever rule? What would you use as your upper bound?
Okay. You're going to use 6.7. This is a line compound.
Okay, so
When you do the lever rule, it's always you look for where it intersects on the left and right. So let's say you're right here at 2. If I, at 2 weight percent carbon at this temperature, if I asked you to do the lever rule there, you'd say, okay, that's my initial composition is 2 weight percent carbon. On the right, 6.7. So if you wanted to say the amount of ferrite, you'd take 6.7 minus 2 and divide that by 6.7 minus whatever that intersect is, which is less than 0.022 by maybe half. It's hard to read.
yeah, I was just making sure it wasn't just cut off in the end. It was actually
Yeah. No, yeah, it's a line compound there. By the way, on the exam, you could, in the past I've had people bring rulers and try and estimate these things. That makes it a nightmare for us to grade. I've done you a favor and I've just written where the intersects are on the midterm. So when you do the lever rule, use the numbers that are provided on the phase diagram. Right? If you see a bunch of little numbers next to intersects, like lines, it's me giving you information to do the lever rule. Okay? Other questions about this, about steel, about the phase diagram of steel, about the phases, reactions that happen? Yeah. Okay. When you do the lever rule, it only works in a two-phase region. You cannot do the lever rule in a single-phase region because the lever rule, by definition, tells you the weight fraction of two phases. Right? And so you can't do it in the liquid region. You could do it up here, right? Say at that little gray spot where it intersects. You could do it right there. You'd look at where it intersects right here, which is about 3.9, 3.8. And on the left, it intersects at about, call it 1.8 or 1.9. Yeah, you could do it that way. Other questions? Everyone clear on the lever rule? Everyone clear on what's the difference between me asking you what's the amount of the phases and their composition? Do you know the difference? Because on the exam, I'm going to say draw the microstructure. Tell me how much of the different phases are present and what their composition is. How would you do that? Amount of the phase we get by what?
I was just going to say the amount of phase would be lever rule and composition would be the weight percent.
Yeah. The lever rule tells you the amount in either weight percent or mole percent, depending on what your graph's given in. But the composition of those phases will be wherever you connected those lines on the side. That's the composition of the phases. Like, what's the composition of iron carbide? Whatever the ratio is, it's going to be 6.7 weight percent. What's the composition of ferrite? Anywhere along this line, it's still just whatever that is. Make sense? The composition is dictated by, if you draw a flat line left to right, where does it intersect boundaries on either side? That's the composition. But the lever rule tells you the amount, and that's a different number. Yeah, question?
So we'll just write down percentages for that, that's the composition?
Yeah, so commonly, like, let's say we wanted to do it right below the eutectoid. Yeah, let's do this. Let's do an example. I want you to tell me the composition of each phase and the amount of each phase, assuming you started at a eutectoid composition, right here, just below the eutectoid reaction. Tell me what's the composition and the amount of each phase. This makes sense what I'm doing here? If I were to ask this, you would first do the lever rule, and just below the eutectic point, we're right here, okay? So if I want to know the amount of ferrite would be 6.7. Oh, I did that backwards. I did that backwards. All right, hold that thought. 6.7 minus 0.76. It's going to give me a different number here. What is that? Somebody's got that? What weight percent does that give us? 6.7 minus 0.76 divided by 6.7 minus 0.022. 88.95. So that tells us that we have almost 90 weight percent of the alpha phase, the ferrite phase, but the composition is not 90%. The composition is wherever it intersects over here, which just below this point is going to be 0.022. Okay? You could do the same thing for cementite. It would be 100 minus 88, right? So it'd be the 11.5 or whatever, 11.1 or whatever it is. Yeah, question?
So just to be clear, of the 88.95 weight percent alpha, 0.022% of that by weight is carbon?
Correct. It's almost entirely pure iron. It only has a little bit of carbon in it. Meanwhile, the cementite is going to have less overall weight fraction of the cementite phase, but it's going to be much richer in carbon, such that if you were to remelt this thing over again, you end right back up at the initial composition, which was 0.76. Okay? Yeah, question, Alex? If you cool it down, good question. So if we keep on cooling this down, like we're not taking the lever rule right here, but we take it down here, assuming it reaches equilibrium, you would have pure iron. All of your carbon would get ejected from the ferrite, and the alpha phase would be pure iron, and in a eutectic structure, but all the cementite would be the same composition that it was before, right? Now, this assumes diffusion, and you're at low temperatures, so it's unlikely you're going to achieve that, right? It's tough to get it to be pure iron like this. And even if you did, remember they're layers, and so how would you separate them? If you wanted to purify iron by doing this, it's tough, because what are you going to do with all the cementite, right? It's a ceramic, which means it's less likely to be dissolvable. The metal's going to dissolve before the ceramic will. So, yeah, that'd be not a great way to separate them, but you could. Hand over there. Landon, is it?
Yeah. So when you ask for the composition, you're not asking for us to write down a formula for like what.
Give me a weight percent of the components.
Say at this point, 88.95% of this stuff is ferrite, and ferrite is 0.022%.
Yeah. Or in other words, when you do these microstructure drawings, it's not complete to just do a drawing and say 50% liquid. You need to tell me the composition of the different phases, as well as the volume, or as well as the weight or the mole fractions. Okay? Any other questions about this? I've given you sort of my summary on low versus medium versus high carbon steel versus ultra high carbon, really cast iron. Some examples of drawing it. What else can I answer about this, or should we move on? Yeah, Fars? Okay. So here's a great example. See, that's a perfect spot to stop right here, right? So this is weight percent copper. You go from aluminum and you dope it with copper. This is a great way to strengthen aluminum. Aluminum is super ductile. You guys have played with paper clips. They bend really easily. What about an aluminum that's a little bit stronger? You like the light weight of aluminum, but you want it to be a little bit stronger. You can start to dope it with things. In this case, they've doped it with a little bit of copper. What they do is they started out at, what is this, like 8 or 9%, something like that, by weight copper, and they heat it up till it's a single phase. That happens above about 500 C. If you go above 500 C, all of that copper will dissolve into your aluminum. So you've got them just mixed randomly everywhere, okay? If you then cool that down, they've got two scenarios, right? It went from being one single phase, you've got two scenarios. There's the ideal and there's the typical, right? And ideal is not thermodynamically ideal. That means for an application ideal. If you want to strengthen something, you typically want what's called precipitation hardening. We will talk way more about this in a couple of chapters. Basically, each one of these little precipitates strengthens the material because of things that we haven't covered yet, right? But more typically is if you don't do this very fast, if it happens quickly, if it does happen slowly, then these are going to accumulate to the grain boundaries, which doesn't give you the same strengthening effect because copper is super ductile itself. Copper and aluminum are both super ductile. So if you've got a ductile material and you've got grain boundaries with ductile materials, that's not very helpful. Whereas if you have a bunch of these little speckles, that gives you the strengthening effect. Okay?
Equilibrium cooling, which one would you?
More like this. Equilibrium means that you're going to get rid of surfaces. Surfaces cost energy. Free energy says lower the energy. That's equilibrium. Right? So if you cooled it really slowly, this is actually hard to achieve, to get it to totally dissolve away, because you're at low temperatures, right? This is happening between 200 and 500 Celsius. That's not very hot. So you don't have much motion. Are there other questions about this? Yeah.
Do eutectoid reactions also form lamellar structures, or is that just eutectic?
Both eutectic and eutectoid both form lamellar structures. Why should they? Why should a eutectoid also form a lamellar structure? Yeah, it still means that you're going from one phase to two different phases that have a different composition, and so that means the atoms have to segregate. That means diffusion, and it's happening all really fast, so it can't happen instantly fast, so they have some finite structure, and you get this lamellar structure. Whether it's eutectic from a liquid to two solids, or from a single solid to two solids, you still get the eutectic structure, or the lamellar structure. Yeah?
So grain regions form when you have two elements or compounds. When you get the zebra pattern?
So in this diagram, if you wanted to form that zebra lamellar structure, could you ever form it at this composition? Yes or no? No. Why can't you ever form it at this composition? Yeah, that flat line up there from 5.65 over to 52.5, that is the line at which you get the eutectic reaction happening. If you're to the left of it, then you'll never get it happening. The best you could do is forming precipitates, maybe, if that's what you were looking for. You couldn't form the eutectic one. So if you wanted some amount of eutectic to form, you'd start moving to the right on that black line somewhere. And the further towards the eutectic point, the larger the fraction of your overall eutectic structure you'll end up with. Right? If you do it, right, let's say you're right here, just on that white line here, if you guys can see that, you're not going to end up with very much eutectic structure. How do we know that? Because we could do the lever rule. Let's do the lever rule. Above that point, tell me what's the weight, let's see, this is in weight percent, so tell me the weight fraction of total eutectic structure you're going to end up with. Okay? Turn to your neighbor, work on this with them. I want the total weight fraction of eutectic, assuming we start at 10 weight percent. So we start, let me make that big. How big do we make this? Okay, we start at 10 weight percent copper and call it 700 C. As we cool to just above the eutectic temperature, how much liquid is left? How much liquid is left? The liquid's on the right, so we're going to take the left-hand segment. Okay, what do you got? How much is left? Just before the eutectic reaction, how much liquid is left by weight? I get about 16%. Somebody else getting about 16 weight percent. Therefore, to answer your question, Ryan, how much eutectic structure could we end up with? No more than 16%. Because the eutectic reaction means that as you cross that line, as you cross this line, the eutectic reaction means liquid going to two phases. So if you've only got 16% liquid at that point, right here, then at best only 16% of your final product will be the eutectic structure. Make sense?
So would it just be like a solid and then an inch?
Yeah. And it looks kind of like this, right? This is up higher. We're over here, but it'd be like big islands that are almost connected with only 16% of this represented by liquid. So in between those islands of alpha, you would have the zebra phase between those. Cool? Ebza?
So when you say just above
So you're just above it, just barely. Or in other words, your flat line is essentially this line, right here to here. If it was just below, then it would be all the way to here. That make sense? Because we're in this quadrant, so we're just barely above that line right here. So we're going from 10 minus 5.65. We're dividing that by 33.2 minus 5.65, and that gives you the 16%. Okay? Okay, 4 minutes left. Can you burn 4 more minutes, or do we start another chapter? Who's got one last question for us? I don't want to start chapter 9 without. Yeah, Sam, what do you got? Landon, what do you got?
So I just wanted to clarify on the phase diagrams. So on the structures. So why is it that like when it's going down and it has the speckles, that all of a sudden the speckles go towards that middle third part, like the middle lines?
Why you started out at this, you crossed over this line, so you now have a thermodynamic driving force to go from pure alpha to alpha plus something else. They call it theta, right? That's what these little theta particles are. Now you're saying, why does it go from here to here?
Yeah, so they just slowly start to move because of the surface tension?
Yeah, if you surface energy, not tension, right? If you added up all the surfaces on a bunch of small things, you get a much larger surface area than if you added up the surface on this. When things coalesce, little tiny particles have high surface area, right? This is why they use carbon filters in your water. If you filter your water, they grind carbon up tiny because it's easy to do it. You basically burn it, and it's already tiny. And then toxins, heavy metals, things that you don't want in your water will adsorb. They'll stick to the surface of those carbons because you have enormous surface area by grinding it up. If I took a diamond, which might weigh just the same amount as the carbon in there, the surface area is tiny. It's way less. So it's the same phenomena. Here you've got lots of surfaces. Here you've got fewer surfaces, and surfaces cost energy. So that's why it wants to go from this to that, but it takes time and temperature to do so.
That's part of why the lower you are on the phase diagram, the lower your Gibbs free energy is because your entropy is becoming lower. Is that
That's not an always true statement. Enthalpy can be increased or decreased as a function of temperature. There's not like a general rule there. Entropy generally increases with temperature because things vibrate more, but enthalpy you can't say the same there.
So after time, it'll go from the speckles to that one?
Yep. Okay, we got time for one last question. Two. Alex, then Sam, and then we're done.
Number 26 on the homework talked about vacancy.
Oh, so 26, the homework problem on that, if you tried it, you got full credit. It's a hard question. It was meant to make you think a little bit. We will talk way more about defects and vacancies in a few chapters. This was meant to make you start thinking about it. So you got credit no matter what you did. And then Sam?